Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to gently tiptoe into one of the most mysterious journeys ever imagined. We're not racing towards answers, but rather drifting through the vast, quiet expanse of the cosmos, where every star is a word in a story we're just beginning to read. But don't worry. This isn't a lecture on complex physics. It's a quiet walk under a sky full of wonders. Imagine yourself wrapped in a soft blanket, looking up at the inky blackness. We'll turn down the bright lights and simply sit with the big, beautiful questions that have captivated humanity for all of time. Tonight, the silence is our classroom, and the moon is our gentle guide. Let us begin. Let us begin our journey with a single profound observation. Our universe is not still. It is not a fixed painting, but a living, breathing thing. For every moment that ticks by on your clock, the fabric of existence itself is stretching, expanding, and unfurling into an ever greater expanse. This isn't an explosion that happened in a distant corner of space, scattering everything outward from a central point. That's a common and understandable mistake to make. Instead, imagine blowing up a balloon with little dots drawn on its surface. As you inflate the balloon, the dots all move away from each other. They aren't crawling across the rubber. The surface itself, the very fabric of their world, is stretching between them. This is a quiet, gentle, relentless movement, the soft, steady hum of the universe growing. It is a constant, almost imperceptible whisper that echoes through every galaxy, every star, and every whisper of starlight that reaches our eyes. This silent, ongoing expansion is the very first mystery we will explore, and it sets the stage for all the others. Because within this expanding ocean of space, there is a restless hum, a constant chorus of phenomena that challenge our very existence. What if there is life beyond our blue planet, thriving in conditions we can barely imagine? What secrets do the stars hold about the origins of our universe and our place within it? We're not meant to have all the answers tonight. Instead, we'll simply let these questions be like fireflies in the twilight, beautiful, mysterious, and full of a soft inner light. Our journey is not about finding the end of the road, but about enjoying the view from the path itself. Our universe, as vast as it is woven from threads of both the seen and the unseen, the tangible and the profoundly mysterious. It is a tapestry where the most visible threads, the stars and galaxies, are held together by a great, invisible scaffold. For a long time, we thought we knew the full picture. We saw the spinning galaxies, the fiery stars, the swirling nebulae, and believed that what we saw was all there was. But when we looked a little closer, when we measured the speed at which things were moving, we found something utterly astonishing. The outer edges of galaxies were spinning too fast. They should have flown apart like a child being spun too quickly on a carousel. An invisible hand, a ghost of gravity, was holding them together. We call this phantom presence dark matter. It doesn't emit light, it doesn't reflect light, and it doesn't interact with anything we can see. It is the great silent architect of the cosmos, building the skeleton around which all the visible, beautiful structures we cherish are formed. Imagine walking through a vast, dark forest at night. You can't see the trees, but you can feel their presence. You can feel them guiding you, shaping your path, and holding the forest together. That is a little like how dark matter works. It is the quiet, invisible hand that holds our universe together. And while dark matter holds things together, there is another mysterious force that is gently, but powerfully, pushing everything apart. When we looked at the most distant galaxies, we found something that went against all of our previous beliefs. We had long assumed that the expansion of the universe was slowing down, pulled back by the collective gravity of all the matter within it. We expected to see the universe putting on the brakes like a car coasting to a stop. But the truth was a breathtaking surprise. It wasn't slowing down, it was speeding up. The car was pressing the gas pedal harder and harder. We call this accelerating push dark energy. It is a force we know almost nothing about, a quiet, insistent pressure that seems to be a property of space itself. As space expands, it creates more of this dark energy in a strange, self-perpetuating cosmic cycle. This is not a force that screams or roars. It is a force that whispers, and its whisper is shaping the very future of everything that exists. Dark energy is one of the most substantial enigmas in all of contemporary cosmology, and its whisper has us questioning everything we know about the ultimate fate of the universe. As we drift deeper into this ocean of ideas, we will find that these unseen forces are not the only mysteries. The universe is also home to some of the most extraordinary and tangible phenomena imaginable, each one an invitation to quiet wonder. Let us turn our attention for a moment to the most intriguing phenomena in the universe, the black holes. They are often spoken of as cosmic devourers, but it is more beautiful to think of them as regions in space where gravity is so strong that even light, the fastest thing we know, cannot escape. These are not hungry beasts. They are simply the inevitable collapsed cores of massive stars. Imagine a star living its fiery life, burning brightly for millions or billions of years. At the very end, when it runs out of fuel, it can no longer support its own immense weight. The star collapses under its own gravity, not into a little point, but into a point of infinite density, a place we call a singularity. Surrounding this singularity is a boundary, a place of no return, known as the event horizon. It is the point beyond which our current understanding of physics simply breaks down. It's like reaching the edge of a map where the words, "Here be dragons," are written. What lies beyond this event horizon is a great and beautiful mystery, a profound question that hangs in the silent darkness of space. In our journey, we will also encounter the extraordinary phenomenon of neutron stars. If black holes are the quiet, mysterious endings of the most massive stars, then neutron stars are the incredibly dense, impossibly heavy remnants of slightly less massive stars. These stellar remnants are so dense that a sugar cube-sized amount of neutron star material would weigh as much as all the people on Earth combined. To even begin to grasp this, you must try to imagine an entire mountain range squeezed into a single grain of sand. The intense gravitational forces within neutron stars create a state of matter known as degenerate matter, where protons and electrons are pressed together so tightly that they merge to form neutrons. And some of these spinning neutron stars, known as pulsars, emit beams of radiation. They are like cosmic lighthouses, spinning rapidly and casting their light across the cosmos in a regular, rhythmic pulse. The very existence of these objects challenges our theories of matter and forces, forcing us to consider a type of matter that is beyond our earthly comprehension. The universe is a great poet, and these neutron stars are one of its most beautiful and mind-bending verses. But not every child of a star gets to stay in a family. In the vast, dark emptiness of the cosmos, there are lonely wanderers, celestial bodies that have been cast out from their stellar homes. We call them rogue planets. These planets wander the cosmos without being tethered to any star, living their existence in the quiet, profound darkness of interstellar space. They may have formed around a star just like our own Earth before being ejected due to violent gravitational interactions with other larger planets. Imagine a solar system in its chaotic youth, with young planets interacting like children at play, bumping and jostling until one is flung out into the cold, quiet void. Or perhaps some of these rogue planets form in isolation, coalescing from the cold gas and dust that permeate space, never knowing the warmth of a star. These are not desolate wastelands without the potential for life. The quiet warmth from their own molten cores could be enough to sustain a subsurface ocean, a hidden world beneath a shell of ice where life could flourish in environments very different from our own. They remind us that the universe is far more creative and full of possibilities than we could ever imagine, and that the existence of a star is not always a prerequisite for the story of life to begin. And as we continue to drift through these mysteries, let us consider for a moment a sensation we could not feel, but one that has completely reshaped our understanding of the universe. For a long time, our view of the cosmos was limited to what we could see, the light that came to us from distant stars and galaxies. But in 2015, we discovered a new sense, a new way to listen to the universe's stories. We detected gravitational waves, which are ripples in the very fabric of space-time itself. Albert Einstein first predicted their existence in 1916, but for a century they were just a beautiful, quiet theory. The first successful detection came from the collision of two black holes, a monumental cosmic event that happened more than 1 billion light-years away. It was a cosmic duet, a final violent embrace between two giants that sent a tremor through the very silence of space. We couldn't hear it, but we could feel it, a faint, almost imperceptible ripple that traveled all the way across the cosmos to reach our planet. The detection of this tremor opened up a new era of gravitational wave astronomy, allowing us to gain insights into celestial phenomena that were previously hidden from our view. It's a bit like listening to the ocean before we only saw the light on the surface, but now we can feel the deep rolling currents below. This new way of listening has not only verified one of Einstein's most profound predictions, but has also given us a brand new sense with which to explore the universe, helping to illuminate the secrets that lie within it. Each of these remarkable phenomena, from the seen to the unseen, from the known to the profound mysteries, invites us to delve deeper into the cosmos. They are not merely scientific puzzles to be solved. They are poems written in the language of physics, a testament to the fact that we do not have all the answers. The true beauty of our journey tonight and of our place in the universe is that we are not at the end of the road. We are at the very beginning of a long and wonderful journey of quiet contemplation. The universe is not a finished book, but a vast library, and we are just learning to read the first few sentences. The most beautiful thing we can do is to simply sit with these wonders, to allow them to fill our minds with a sense of awe, and to find a comfortable and beautiful home in the act of not knowing. The journey is the destination, and tonight we are simply taking the first gentle steps together into the quiet majesty of it all. Let us drift a little further beyond the gentle hum of the expanding cosmos and into the stories of its most dramatic characters. We will begin with a final act, a cosmic ballet of collapse and creation, leading us to one of the universe's most enigmatic and feared phenomena, the black hole. To truly understand a black hole, we must first imagine a star, not a small steady one like our sun, but a star of immense scale, a true celestial titan, burning brightly for millions of years. This giant star is in a constant, delicate balance. Its internal nuclear fires push outward, resisting the immense inward pull of its own gravity. For a while, the two forces hold each other in perfect check, but all stories, even those of stars, must end. When the star exhausts its nuclear fuel, the outward pressure vanishes. There is no longer anything to hold back the relentless crushing force of gravity. In a final spectacular finale, the star may undergo a supernova explosion, a cosmic fireworks show that momentarily outshines an entire galaxy, shedding its outer layers into space. But at the heart of this explosion, something else is happening. The star's core, now a dense remnant, continues to collapse under its own gravity. It is an unstoppable descent, a fall into an abyss of its own making. This is not a collapse to a tiny solid sphere. This is a collapse to a point of infinite density, a place we call a singularity. Here, our current laws of physics simply give up. They break down. The mathematical equations that describe everything we know about space-time and matter cease to make sense. We are left standing at a shoreline, looking out into an ocean whose depths we cannot measure, whose properties we cannot describe. The singularity is a mystery so profound that it humbles even the most brilliant minds. It's the ultimate what if, a question mark at the very center of creation. What lies inside this point of infinite density? Is it the end of space and time as we know it? Or is it a doorway to somewhere or somewhere when else we don't know? And perhaps that is the most beautiful part of all. Around this singularity, like the perimeter of a great cosmic lake, is the event horizon. This isn't a physical wall or a visible surface. It's a boundary, a point of no return, a last moment to look back and say goodbye. Imagine a gentle river flowing toward a waterfall. As you drift, the current becomes stronger and stronger. At some point, the river flows so fast that no matter how hard you paddle, you can no longer turn back. That point is the event horizon. Everything that crosses this threshold, whether it's a particle of dust, a beam of light, or the very fabric of space-time itself, is irrevocably drawn inward, destined to meet the singularity at the core. The enigmatic nature of black holes stems from the very essence of their existence. They challenge our understanding of physics, particularly at the intersection of general relativity and quantum mechanics. The immense gravitational pull warps space and time around them. And what happens to the information that crosses the threshold remains a captivating puzzle. Information that crosses this boundary appears to vanish, igniting debates among physicists about the fundamental concepts of space-time and reality. Now let us turn to a different kind of celestial story, one that is not of finality, but of impossible endurance. When a massive star, one slightly smaller than the ones that become black holes, reaches the end of its life, it also explodes in a supernova, but its core does not collapse into a singularity. Instead, it collapses into an object of unimaginable density, a neutron star. These stellar remnants are so dense that if you were to take a single teaspoon of their material, it would weigh as much as all the people on Earth combined. To even begin to picture this, imagine an entire mountain range squeezed into a single, tiny sugar cube. The sheer scale of this compression defies our everyday comprehension. The intense gravitational forces within neutron stars create a state of matter known as degenerate matter, a bizarre state where protons and electrons are forced to merge, creating a solid mass of neutrons. It is a subatomic pileup on a cosmic scale, a place where the rules of normal matter cease to apply, and new exotic physics takes over. This incredible density is not a silent, static thing. Many of these neutron stars are spinning at astonishing speeds, sometimes hundreds of times a second. As they spin, they emit powerful beams of electromagnetic radiation from their magnetic poles. If one of these spinning beams happens to sweep across our line of sight, we see a regular repeating pulse of light. We call these cosmic timekeepers pulsars. They are the cosmic metronomes, their pulses so regular and precise that they can be used as clocks. They are the lighthouses of the deep, a rhythmic, steady beat in the profound silence of space. Observing how these dense objects behave challenges our current theories of matter and forces, forcing us to reconsider existing models and pushing the boundaries of physics and astronomical observation. They provide a laboratory for the most extreme physics imaginable, teaching us about the behavior of matter under pressures we could never hope to recreate here on Earth. They are a testament to the universe's ability to create wonders far beyond our most vivid imaginations. Not every celestial body is born from such fiery drama. Some wander alone, orphan children cast out from their homes. We call them rogue planets. These planets are celestial nomads wandering the cosmos untethered to any star. Their journey is one of quiet, profound loneliness. They may have formed around a star as our own Earth did, but in the chaotic youthful years of a solar system, a violent gravitational interaction with a larger planet could have flung them out into the cold, dark void. Or equally compellingly, they may have formed in isolation, coalescing from the cold, gas and dust that permeate the space between stars, never knowing the gentle warmth and light of a sun. This quiet, dark existence does not mean they are necessarily without the potential for life. Beneath a shell of thick ice, a rogue planet might hold a vast subsurface ocean, kept liquid by the quiet, steady warmth of its own internal geological forces. In this deep, dark ocean life could flourish, perhaps powered not by sunlight, but by geothermal vents on the ocean floor. Much like the extremophils we find in the deepest, darkest parts of our own oceans. The possibility of life on such a world challenges our preconceptions about what a habitable planet looks like. It suggests that the universe is far more creative and full of possibilities than we could ever imagine, and that life in its inherent stubbornness might find a way to thrive in the most unexpected places. And finally, as our minds grow quiet and our thoughts become still, let us consider the profound echo of a silent event. For centuries, our view of the universe was limited to what we could see, the light that came to us from distant stars and galaxies. But in 2015, a new window to the cosmos opened. We detected gravitational waves, which are ripples in the very fabric of space-time itself. Albert Einstein first predicted their existence in 1916 as part of his theory of general relativity, but for a century, they were just a beautiful, quiet theory. The waves are incredibly faint, a tiny stretching and squeezing of space-time on a scale smaller than an atom. Detecting them required building an almost impossibly perfect instrument, a long, quiet observatory with 2 arms stretching for miles. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was built to listen for the universe's whispers, to feel the subtlest tremors passing through us. The first tremor was detected in September 2015. It was the echo of a cosmic ballet that had happened over 1 billion years ago, the final moments of 2 black holes spiraling in toward each other, accelerating in a death dance before merging into one. The collision released a colossal amount of energy in the form of gravitational waves, a single magnificent cosmic duet that was felt throughout the universe. We couldn't hear it in the traditional sense, but the tremor was felt and recorded by our instruments. This was more than just a confirmation of a century-old prediction. It was a revolution in astronomy. It opened up a completely new way of observing the universe, a new sense beyond sight. Unlike light, which can be blocked or absorbed by matter, gravitational waves pass through everything unhindered. They give us a glimpse into phenomena that were previously hidden from our view, a way to listen to the universe's most dramatic moments without a single sound. The ability to detect these waves has since expanded with new observatories, joining the quest to observe and analyze the messages these waves carry from deep within the cosmos, helping to illuminate the secrets of our universe. The journey to understand these phenomena is not just a scientific one. It is a journey of quiet contemplation, a deepening of our collective sense of wonder, and a profound realization that the universe is far stranger, more mysterious, and more beautiful than we could ever have imagined. As we drift further into the great cosmic quiet, let us turn our attention from the dramatic to the subtle, from the fiery remnants of stars to the gentle unseen forces that shape the universe itself. Our journey now takes us to the vast silent architecture of the cosmos, a structure held together by something we cannot see, feel, or touch yet, whose presence is as certain as the stars themselves. This is the realm of dark matter, a profound puzzle that whispers to us of a universe far bigger and stranger than the one we perceive with our eyes. For a long time, we were like people in a dark room, seeing only the glowing embers of a fire and assuming, that's all that existed. We looked at galaxies and saw their light, a beautiful spiral of stars, gas, and dust. But when we measured their spin, we found a deep and beautiful paradox. The stars on the outer edges of a galaxy were rotating far too quickly for the amount of visible matter we could see. By all the laws of physics, we know those stars should have been flung off into space like drops of water from a spinning wheel. But they weren't. Something was holding them together, a silent, invisible hand with an immense gravitational grip. This missing mass, this ghostly presence, is what we call dark matter. It is a vital component in the architecture of the cosmos, influencing the formation and behavior of galaxies in profound ways. Imagine a child's mobile with beautiful, brightly colored planets hanging from a delicate wire frame. Now imagine if the planets were spinning so fast that the wires holding them should have snapped. The only explanation is that there is an invisible, much stronger wire frame holding it all together. Dark matter is that invisible scaffold, the cosmic skeleton upon which the magnificent structures we see are built. Without it, the universe, as we know it, would simply fly apart. This intangible mass influences the rotation of galaxies and the formation of large-scale structures in the universe, a phenomenon leading scientists to question what it truly is and how it interacts with ordinary matter. The search to uncover the nature of dark matter pushes the boundaries of physics and forces researchers to reconsider existing models. We know it's there only through its gravitational effects on visible matter. It is the ultimate ghost in the machine. Observations reveal that galaxies are surrounded by vast halos of dark matter which significantly affect their structure and evolution. As galaxies formed in the early universe regions with higher concentrations of matter began to collapse under their own gravity. Dark matter played a crucial role in this process, acting as a gravitational framework or a scaffold around which normal matter could clump together. This framework allowed gas and dust to coalesce, forming stars and other celestial bodies. Therefore, the existence of dark matter not only facilitates the birth of galaxies, but also contributes to the formation of large-scale structures in the universe, such as galaxy clusters. Our current theories tell us that dark matter makes up approximately 27% of the universe's mass energy content. But what it's actually made of remains one of the most profound questions in all of science. We have built deep underground labs, shielding our sensitive detectors from all earthly noise, waiting for a single dark matter particle to finally interact and reveal itself. This is a quest that requires immense patience and an acceptance of the beautifully unknown. But while dark matter is quietly holding the universe together, there is another even more mysterious force that is gently but powerfully pushing it apart. This is the phenomenon of cosmic acceleration, which brings us to a new frontier of mystery dark energy. For a long time, we assumed that after the initial cosmic push of the Big Bang, the collective gravity of all the matter and dark matter in the universe would be acting as a cosmic brake, slowly slowing the expansion down. We expected the universe to be coasting to a stop, or at least to be decelerating. But in the late 1990s, observations of distant supernovae, which are incredibly bright stellar explosions, revealed something truly breathtaking. These cosmic lighthouses were dimmer than they should have been, which meant they were further away than our models had predicted. The universe's expansion wasn't slowing down. It was speeding up. It wasn't putting on the brakes. It was pressing the gas pedal. This profound discovery necessitates the inclusion of a form of energy known as dark energy, which constitutes about 70% of the universe's content. Its properties and origins remain one of contemporary cosmology's most substantial enigmas, fueling discussions about the fate of the universe and the fundamental forces at play. The nature of dark energy is a quiet, powerful mystery. One prominent theory, known as the cosmological constant, suggests that dark energy is not a force in the traditional sense, but an inherent property of space itself. As space expands, it creates more of this push. The more space there is, the more dark energy there is, and the faster the expansion goes. This is a self-perpetuating cycle, and its implications for the universe are immense. Our ultimate fate, it seems, depends on the nature of this silent push. If it continues to accelerate the expansion, the universe will continue to grow colder and more sparse, an end state known as the Big Freeze. Galaxies will drift so far apart that the light from them will never reach us. The stars will eventually burn out, and the universe will become a dark, silent, lonely place. Or in a more dramatic scenario, if the dark energy strengthens over time, the expansion could become so intense that it would tear galaxies apart, then stars, then planets, and eventually even atoms themselves in a violent end state known as the Big Rip. These are not just scientific possibilities. They are profound poems about the future of everything that exists. Now let us turn to an idea that is so elegant and beautiful, it feels more like music than science. We have two pillars of modern physics, general relativity, which describes the universe on the grandest scales, planets, stars and galaxies, and quantum mechanics, which describes the universe on the smallest scales, atoms and particles. For a long time, these two theories have been incompatible, like two magnificent pieces of a puzzle that simply won't fit together. One of the most promising ideas for a theory of everything that could unify them is string theory. At its core, string theory posits that the most basic building blocks of our universe are not point-like particles, but rather tiny vibrating strings. Imagine a violin string. The note it plays depends on how it vibrates. In string theory, an electron is a string vibrating in one way, a photon in another, and so on. The different vibrations correspond to different particles, creating a beautiful unifying framework for all matter and energy. This concept, so profoundly simple and yet so complex, has led to some truly mind-bending ideas. One of the most profound implications of string theory is the possibility of extra dimensions. We live in a world of three spatial dimensions: up, down, left, right, forward, backward, and one dimension of time. But to make the mathematics of string theory work, it often requires the existence of many more dimensions, perhaps 10 or even 11. These extra dimensions aren't visible to us. They are curled up or compacted into tiny microscopic spaces at every point in our universe. Imagine a tightrope walker on a long, thin rope. To the walker, the rope is a one-dimensional line. But to a tiny ant crawling on the rope, it has an extra dimension around its circumference. We are the tightrope walkers, and the extra dimensions are the tiny circumferences that we are too big to perceive. This thought challenges our traditional understanding of reality and opens new avenues for inquiry into the nature of existence itself, suggesting that our universe could be just one of many, with strings vibrating in different ways, possibly giving rise to entirely separate realms of existence, what we call a multiverse. And this brings us to a final quiet question about beginnings. We have been told the story of the Big Bang, a moment when the universe began from an incredibly hot, dense state. But what if that wasn't the beginning? What if there was something before the bang? The idea of a cyclic universe suggests that the cosmos undergoes endless cycles of expansion and contraction, rather than being bound to a singular beginning and eventual end. This intriguing idea suggests that our Big Bang may have been a big bounce, the explosive rebound from the collapse of a previous universe. A universe that breathes in and out, collapsing under its own gravity, and then springing back to life in a new Big Bang. This narrative, a universe that is a perpetual phoenix rising from its own ashes, is a deeply beautiful and profound thought. While these theories remain speculative, they provide an attractive narrative that aligns with some astrophysical observations, suggesting that the universe may not have started merely at the Big Bang, but instead could be part of an eternal series of transformations. The patterns in the cosmic microwave background radiation, a faint echo of the Big Bang, might even hold whispers of a previous existence, a cosmic archaeology that we are just learning to read. Each of these ideas, from the invisible scaffolds of dark matter to the elegant strings of a universe reborn, asks us to look beyond our assumptions and to find a profound and quiet wonder in the mysteries that surround us, a gentle journey into the unknown. As our thoughts settle into the quiet hum of the cosmos, let us turn our attention from the grand unseen forces and journey into a different kind of mystery, one that touches the very heart of what it means to be alive. We will now gently drift into the question that has captivated humanity for all of its existence: are we alone? To begin to answer this, we must look beyond our own sun and our own family of planets. For many years, the notion of other worlds, especially those that might be populated with life, was confined to the realm of science fiction, a beautiful dream of what might be. But the last few decades have rewritten this story entirely. We now know that our sun is not unique in its planetary family. The discovery of exoplanets, or planets, that exist outside our solar system fundamentally alters our understanding of the universe. The realization that there are billions of stars, each a potential sun, and that many of them host multiple planets, radically expands the scope of our cosmic neighborhood. It's like we once believed our small town was the only one in existence, only to look over the hill and see an entire continent of cities, all waiting to be discovered. The diversity of these exoplanets has shattered our previous preconceptions about what planetary systems can look like. We have found hot Jupiter's gas giants that orbit their stars at blistering speeds, and we have found super-Earth's planets far more massive than our own. From gas giants to Earth-like planets, these discoveries encourage scientists to rethink planetary formation theories, revealing an astonishing variety of atmospheres, terrains, and potential habitability. Astrophysicists estimate that in our Milky Way galaxy alone, there could be as many as 100 million planets within the habitable zone, a region where conditions may be just right for the existence of liquid water. A vital ingredient for life as we know it, this highlights the possibility that we are not alone and that there may be numerous places across the cosmos where life could exist, thriving in environments very different from our own. Now let us consider a profound and quiet possibility. What if life isn't just something that starts on a planet, but something that travels between them? This idea, known as panspermia, suggests that life may not be restricted to just one planet, but could instead travel across the cosmos, hitching a ride on asteroids, comets, or even interstellar dust particles. Imagine tiny microscopic life forms such as bacteria or spores, so resilient that they could survive the extreme conditions of space, the vacuum, the freezing cold, and the harsh radiation. Protected within the safety of a rock, these tiny organisms could be blasted off a planet's surface by a powerful impact, then drift through the vastness of space for millions of years before eventually crashing onto a new fertile world, a cosmic seed planting a new beginning. The discovery of extremophilous organisms on Earth that thrive in the most hostile environments imaginable, from deep-sea hydrothermal vents to frigid polar regions, bolsters this idea. These creatures have shown us that life is far more persistent and adaptable than we ever thought, suggesting they could endure the harsh journey through space. The implications of panspermia extend beyond simple survival. They challenge our understanding of biology and the very nature of life itself as a cosmic phenomenon. It raises the beautiful, quiet thought that all life in the universe might be connected a single cosmic family. But how do we begin to wrap our minds around the sheer probability of life in the universe? This is where a quiet, thoughtful framework comes into play. The Drake equation, proposed by astronomer Frank Drake in 1961. This equation is not a formula for a final answer, but a beautiful way to organize our ignorance. It is a thought experiment that attempts to estimate the number of civilizations within our galaxy with which we might be able to communicate. It takes into account various factors such as the rate of star formation, the fraction of those stars that have planets, the number of planets per system that could support life, and the likelihood of life developing and evolving on those planets. It is a series of quiet, humble questions. How many stars are born each year? How many of those stars have planets? On how many of those planets does life actually begin? On how many of those planets does that life become intelligent? And how long does that intelligent life last? Each term in the equation represents a deep mystery, a frontier of uncertainty that scientists are eager to explore. The equation underscores the importance of technological development and global collaboration in searching for extraterrestrial signals, reminding us that we are part of a much larger cosmic story. The Drake equation also leads us to a profound, quiet paradox that was first voiced by physicist Enrico Fermi. If the probability of life is so high, where is everybody? This is the Fermi paradox, and it juxtaposes the high probability of extraterrestrial civilizations existing somewhere in the universe with the glaring lack of evidence for or contact with such civilizations. The universe is ancient and vast, containing billions of galaxies and countless stars, many of which likely host planets in the habitable zone. Given these staggering numbers, one would expect to see signs of intelligent life. Yet despite extensive searching, we find ourselves seemingly alone in this cosmic expanse. The paradox invites us to ponder whether intelligent civilizations inevitably self-destruct before they can venture into the stars or communicate across the vast emptiness of space. This is a sobering thought, a cosmic warning. The paradox also highlights our own place within this grand cosmic theater, urging us to reflect on the sustainability of our civilization and the importance of safeguarding our planet. The search for answers to this profound silence is not just about looking outward. It is about looking inward and asking ourselves what it means to be a sustainable, peaceful, and long-lasting species. The paradox is both a source of hope and a profound challenge, and it reminds us that we are still in the very earliest stages of our cosmic journey. As we lie here letting these questions wash over us, let's consider the practical side of this great search. Our current efforts to find life are a delicate dance of technology and patience. We are using new and powerful telescopes, like the James Webb Space Telescope, to peer into the atmospheres of distant exoplanets. We're not just looking for the planets themselves, but for what they're wearing, the chemical signatures of their atmosphere. We're looking for gases that shouldn't be there naturally. Gases that might be produced by a living, breathing world. The presence of gases like oxygen, methane, or carbon dioxide in an atmosphere can be a potential biosignature, a hint of biological activity similar to what we see on Earth. But the search for life isn't limited to a simple checklist. The universe, in its quiet wisdom, is likely to have invented life in ways we can't yet imagine. The life we find might not be carbon-based, might not use water, and might not breathe in and out as we do. It might be a life so different that we wouldn't even recognize it as life at all. The search is therefore also a journey of expanding our own imagination, of letting go of our assumptions about what life should look like, and opening our minds to the incredible diversity of a universe we are just beginning to know. This gentle journey has taken us through some of the biggest questions of all. We've considered the possibility of other worlds and other lives, and we've sat with the quiet, profound silence of the universe. The mystery is not a flaw. It is the very essence of our cosmic adventure. It is the reason we continue to look up at the night sky, to let our thoughts drift through the constellations, and to feel a sense of connection to everything that is out there. The quiet contemplation of these mysteries is an act of hope and an act of humility. It is a reminder that we are small, but our curiosity is vast, and in the silent expanse of space, that curiosity is our most precious and powerful guide. As we close our eyes and let the stars fade from our mind's eye, we carry with us the weight of these questions, not as a burden, but as a promise of a future filled with wonder. As our thoughts settle into the quiet rhythm of the cosmos, let us turn our attention from the grand search for extraterrestrial civilizations and gently shift our focus to the very definition of life itself. What does life look like? What does it need to survive? For a long time, we have assumed that life must be like us, carbon-based, water-dependent, and breathing a familiar atmosphere. But our universe, in its quiet and profound wisdom, is far more creative than our imagination allows. To begin to understand what alien life might be, we must first look to the most unexpected corners of our own planet, where life has proven to be a tenacious and resourceful thing. This is the field of astrobiology, a quiet, thoughtful science that uses our understanding of life on Earth to model what alien ecosystems might look like. It is a field that invites us to let go of our assumptions and to open our minds to the incredible resilience of a universe that seems to be in the business of creating life. At the heart of this exploration is the study of extremophiles, remarkable organisms that thrive in some of the most hostile environments on Earth. places where most life forms cannot survive. These resilient beings can withstand extreme temperatures, high radiation levels, acidic or alkaline conditions, and intense pressures. They are the ultimate survivalists, the living proof that life, when pushed to its limits, finds a way. For instance, in the deep dark oceans of our planet, there are hydrothermal vents where superheated mineral-rich water erupts from the Earth's crust. Here, in complete darkness and under immense pressure, entire ecosystems of life flourish. They do not rely on sunlight for energy, but on a process called chemosynthesis, deriving energy from the chemical reactions of the minerals spewing from the vents. This profound adaptability suggests that life can arise in different forms, utilizing varying energy sources, a crucial lesson for our search for extraterrestrial life on moons like Europa or Enceladus, where subsurface oceans exist beneath icy surfaces. The diversity of genetic and physiological traits evident in these oceanic organisms can provide models for understanding how life might evolve under varying extraterrestrial conditions. They are a living playbook for the possibilities of alien biology, a gentle whisper from our own planet about what might be possible elsewhere. This brings us to two of the most tantalizing mysteries in our solar system: Europa, one of Jupiter's moons, and Enceladus, one of Saturn's. Both are small icy worlds that on the surface seem entirely inhospitable, but beneath their thick cracked shells of ice, scientists believe there lie vast global oceans of liquid water. Europa's ocean is thought to be kept warm through tidal heating, generated by the immense gravitational pull of Jupiter and its other moons. This constant kneading of the moon's interior creates enough heat to prevent the ocean from freezing solid, providing a stable, life-sustaining environment beneath the protective icy shell. Enceladus is even more dramatic. Scientists have observed geysers erupting jets of water vapor and ice particles from its southern pole, a direct, tantalizing window into the subsurface ocean below. These plumes contain not just water, but organic molecules, the very building blocks of life. These observations made by missions like Cassini are like a free sample, a quiet invitation from Enceladus to study what lies beneath its icy exterior. The chemistry occurring on moons like Titan, Saturn's largest moon, with its dense atmosphere and lakes of methane and ethane, is vastly different from that on Earth. Yet it opens the door to exploring alternative forms of life that might exist. These moons offer a glimpse into environments that diverge from our terrestrial experience. The exploration of these celestial bodies could revolutionize our understanding of the potential for life in the cosmos and the processes that govern the evolution of water worlds. But let us not forget the planet next door, our silent, reddish neighbor Mars. For centuries, Mars has captivated our imagination, largely due to its potential to have once harbored life. We now know that billions of years ago, Mars was a very different place. Evidence from robotic rovers like Curiosity and Perseverance has unveiled geological features that suggest ancient rivers, lake beds, and possibly even oceans existed on its surface for long periods. The rovers have found carbonates and sulfates embedded in rocks and soil substances often associated with biological processes on Earth. These geological features paint a picture of a past Mars that was warmer, wetter, and possibly more hospitable to life. The search for microbial life is at the forefront of these missions. Our rovers are equipped with advanced scientific instruments designed to analyze soil and rock samples for organic compounds and biosignatures, the telltale chemical signs of a living organism. Additionally, studies of Martian meteorites found on Earth have revealed organic molecules, which are the building blocks of life, raising intriguing questions about the possibility of ancient microorganisms on Mars. While we have yet to find definitive proof, each piece of evidence adds to a growing tapestry of discoveries that increases the likelihood that Mars was once home to microbial life forms. A discovery of past life on Mars would not only confirm that life can exist beyond Earth, but would also challenge our understanding of how life originates and survives in diverse environments. Now, as our journey through these possibilities comes to a close, let's circle back to the core of this quiet contemplation. How do we model and search for this life? Scientists harness the principles of biochemistry to create models of alien ecosystems, a beautiful and thoughtful process that begins by identifying biosignatures, indicators of life, such as specific molecules or chemical patterns that arise from living organisms. By exploring the biochemical functions of various life forms on our planet, researchers extrapolate these findings to hypothesize about what alien biochemistries might look like. Computer simulations play a critical role, allowing researchers to input data about known biochemical processes and environmental variables, creating intricate models that reveal how life might thrive in diverse alien ecosystems. For instance, they consider factors such as temperature, atmospheric composition, and radiation levels, predicting how organisms might adapt over time. Crucially, scientists also factor in the role of elements in the formation of life. While carbon is central to terrestrial life due to its versatile bonding properties, researchers consider other elements like silicon as potential alternatives for biochemistry. This broadens the possibilities for life and ecosystems beyond Earth, suggesting that by understanding biochemistry, we can push the boundaries of what life could be in the cosmos. Ultimately, the search for life is a humbling journey. It forces us to confront our own assumptions and to embrace a universe that is far more wondrous and creative than we could ever imagine. The extremophiles on Earth, the icy oceans of Europa, and the dried-up riverbeds of Mars are all quiet teachers, showing us that life is persistent, resilient, and always finds a way. As we drift off into sleep, we carry these thoughts with us, a quiet sense of hope and a profound appreciation for the sheer stubborn wonder of life itself. The search for life beyond our planet is not just about finding an answer. It is about learning a deeper truth about the universe and about ourselves. It is a journey that changes us, reminding us that in the great silence of space, our small, lonely planet is a testament to the quiet, persistent magic of being alive. As we continue our gentle drift through the cosmic quiet, let us now turn our minds not to the future and its possibilities, but to the past and to the quiet, persistent curiosity that has always defined us as a species. Long before the invention of telescopes or the launch of rockets, our ancestors looked up at the night sky and saw not just a blank canvas, but a storybook, a calendar, and a guide. This ancient human impulse to connect with the heavens is the very foundation of our modern astronomy. Throughout history, various ancient civilizations demonstrated an impressive understanding of astronomy through their technologies and constructions. The Babylonians, for instance, were meticulous record keepers. Night after night, they would observe the movements of the stars and planets, carefully etching their celestial observations onto clay tablets. Their calculations of planetary positions and lunar phases enabled them to develop an early form of astronomy that would influence future civilizations. They saw patterns, predicted eclipses, and began to understand the heavens as a place of order and rhythm, not chaos. This was not a passive form of contemplation. It was an active scientific endeavor driven by a desire to understand their world. Similarly, the ancient Egyptians also played a crucial role in astronomical advancements. The construction of their pyramids was aligned with the stars, particularly with Sirius and Orion, reflecting their deep understanding of the heavens. Egyptian astronomers tracked the annual flooding of the Nile River by observing the heliacal rising of Sirius, which was critical for agricultural planning and daily life. The sky was not separate from their world. It was a living, breathing part of it, directly influencing their survival and their most important rituals. In Mesoamerica, the Maya civilization made extraordinary contributions to astronomy, creating complex calendars based on their observations of celestial bodies. They developed sophisticated techniques for predicting solar and lunar eclipses and meticulously recorded the movements of planets, especially Venus, which held particular importance In their calendrical systems, they constructed massive observatories, allowing them to track the positions of celestial bodies with astonishing precision. Their knowledge was so advanced that it was often interwoven with their religious beliefs, highlighting the intrinsic connection between their cultural practices and the cosmos. And in Europe, the megalithic structures of Stonehenge in England stand as a profound testament to this ancient cosmic curiosity. Constructed around 5,000 years ago, this site exhibits astronomical alignments linked to the summer and winter solstices. The placement of the stones suggests that those who built Stonehenge possessed both observational skills and a deep connection to the cosmos, allowing them to mark time and possibly conduct rituals centered around celestial events. These examples illustrate that advanced knowledge of astronomy was not the sole purview of modern science, but was evident in ancient civilizations throughout history, a testament to a shared human wonder. For many centuries, the dominant view of our place in the cosmos was one of cosmic pride. The ancient Greeks, building upon the observations of earlier civilizations, proposed a geocentric model where the Earth was thought to be at the very center of the universe. This model, most famously articulated by Ptolemy, placed Earth at the center with the sun, moon, and stars revolving around it in perfect concentric spheres. This was a beautiful and elegant idea, one that made perfect intuitive sense. It placed humanity and our planet at the focal point of all creation, and it dominated scientific and philosophical thought for centuries. But then a quiet revolution began. In the 16th century, a Polish astronomer named Nicholas Copernicus had the audacity to propose a new model, a heliocentric model where the sun, not the Earth, was at the center of the universe. This was a radical idea, a silent whisper that would grow into a roar. It was a complete paradigm shift, challenging long-standing doctrines that placed humanity at the center of the divine order. The Copernican revolution was a profound turning point in how humanity perceives its place in the universe. It diminished the perceived significance of Earth and humanity, casting us not as the unique center of creation, but as just one of many celestial bodies orbiting a larger entity. The sense of grandiosity that once enveloped humanity began to fade, replaced by a humbler recognition of our place in an expansive universe filled with countless stars and planets. This new way of thinking laid the groundwork for the most important invention in the history of astronomy, the telescope. In the early 17th century, a brilliant mind named Galileo Galilei turned this new device toward the night sky. What he saw changed everything. He saw the moons of Jupiter, a miniature solar system orbiting a planet, proving that not all celestial bodies revolved around the Earth. He saw the phases of Venus, which could only be explained if Venus was orbiting the sun. And he saw sunspots' imperfections on the face of the supposedly perfect sun. These groundbreaking observations provided the first visual undeniable evidence that the geocentric model was wrong. The telescope was not just a tool. It was a cosmic eye allowing humanity to see the universe in unprecedented detail and forever changing our comprehension of our place within it. The 20th century, however, was a period of such rapid and profound discovery that it completely reshaped the landscape of cosmology. It began with the quiet genius of Albert Einstein and his theory of general relativity. This theory fundamentally altered our perception of gravity, not as a force pulling things together, but as the curvature of space-time itself. His work opened up new avenues for exploring the universe, allowing scientists to understand phenomena such as black holes and the expansion of the universe. This was followed by a moment of cosmic revelation. In the 1920s, an astronomer named Edwin Hubble looked at distant galaxies and found that they were all rushing away from us. The further away they were, the faster they were moving. This was a monumental discovery. It meant that the universe was not static, it was expanding. Hubble's observation of an expanding universe not only transformed our grasp of the cosmos, but also set the stage for one of the most important theories of all, the Big Bang Theory, which describes the origins of our universe from a single incredibly hot and dense state approximately 13.8 billion years ago. The ultimate confirmation of the Big Bang came in the mid-20th century with the discovery of cosmic microwave background (CMB) radiation. This faint afterglow of the universe's birth is a residual heat signature that fills the cosmos, a faded photograph of the universe as a baby just 380,000 years after the Big Bang. This landmark finding not only validated theoretical predictions, but also ignited a new era of observational cosmology, allowing us to glimpse the conditions of the early cosmos. The mid-century also saw the dawn of the space age. The launch of Sputnik, the first satellite, followed by Yuri Gagarin, becoming the first human in space, and finally, Neil Armstrong walking on the moon, were not just technological achievements, they were philosophical leaps. We were no longer just looking up at the universe. We were now a part of it. The images and data gathered during these missions have been vital for understanding planetary geology, atmospheres, and the basic ingredients for life. They allowed us to see Earth from a new perspective, as a small, fragile, pale blue dot in a vast and silent ocean, and the creation of the International Space Station was a beautiful testament to this new perspective, a small shared home in the sky where humanity from different nations could work together toward a common goal. This era of exploration, from ancient observations to modern spaceflight, is a testament to a quiet, powerful journey of the human mind, a continuous story of wonder and discovery. As our journey continues, let us turn our attention from the historical arc of discovery to the modern instruments that are carrying our curiosity into the future. We are no longer limited to the naked eye or even to the visible light that our ancestors used to map the heavens. The last century has gifted us with new senses, new ways to listen to the universe's quiet and profound stories. Our next chapter is a quiet tour of the tools we use and the incredible, sometimes strange whispers they are helping us hear. We begin with an entirely different kind of telescope. For millennia, astronomy was a science of sight, but now it is a science of sound, or rather of listening. Radio telescopes are our giant ears, probing the cosmos by capturing radio waves emitted by celestial objects. Unlike optical telescopes, which collect visible light, radio telescopes are designed to detect these invisible radio frequencies. Cosmic signals can provide insights into various phenomena, including pulsars, quasars, and even the cosmic microwave background radiation, the very echo of the Big Bang. A radio telescope's large dish acts like a collector, gathering these faint signals and translating them into data that scientists can analyze. By studying the frequency, intensity, and timing of these waves, researchers can gain clues about the structure and behavior of the universe. This multi-frequency approach to cosmic exploration provides an invaluable perspective on the universe, helping to unravel its mysteries while expanding our understanding of its origins and evolution. One of the most captivating applications of radio telescopes has been the search for extraterrestrial intelligence, or SETI. These instruments continuously scan the sky for unusual signals that are not easily attributable to natural cosmic phenomena. Imagine the challenge, listening to a vast, silent cosmic ocean, hoping to catch a single meaningful word. The infamous wow signal. A powerful, unexplained radio signal recorded in 1977 remains a famous example of this kind of tantalizing mystery. It was a signal so strong and so unusual that it sparked a wave of curiosity and investigation, a cosmic question mark that has yet to be answered. The effectiveness of radio telescopes lies in their ability to penetrate cosmic dust clouds and gas that often obscure visual observations, giving us a perspective that no optical telescope could ever achieve. But the data from these cosmic ears and eyes is vast, often amounting to hundreds of terabytes every day. No human mind could ever hope to sift through all of it. This is where a new and powerful partner enters the story: artificial intelligence. AI is becoming an indispensable tool in the exploration of cosmic mysteries. AI algorithms can process this data at incredible speeds, identifying patterns and anomalies that human researchers might overlook. This capability opens up new avenues for discovering celestial phenomena from exoplanets to the remnants of ancient stars. In the quest to detect exoplanets, for instance, AI can analyze light curves from distant stars looking for tiny dips in brightness caused by a planet transiting in front of its star. By employing machine learning techniques, these systems can improve their accuracy over time, becoming adept at distinguishing between genuine signals and noise. This approach has proven so effective that it has contributed to the identification of thousands of new exoplanets in our galaxy. AI is our tireless assistant, our ever-watchful sentinel, helping us to see the cosmic forest for all its individual trees. The last few decades have also seen the dawn of a new kind of space race, one not between nations, but between private companies. This is the era of the private explorers. Companies like SpaceX, Blue Origin, and Virgin Galactic have become pivotal players in cosmic exploration, significantly enhancing the scope and pace of our ventures into the universe. With their innovative approaches, they are not only reducing costs, but also increasing access to space for diverse scientific missions. The development of reusable rocket technologies by these companies allows for a dramatic decrease in the expense of launching payloads into orbit, thereby making space more accessible for scientific research and exploration. This new synergy advances scientific knowledge and builds a more robust presence in space. These private firms are also venturing beyond low Earth orbit, setting their sights on the Moon and Mars, and their ambitious plans are inspiring a new generation of scientists and engineers to pursue careers in space exploration. This private sector dynamism brings a fresh energy to cosmic exploration, revealing possibilities that were once confined to our imagination. And as we peer deeper into the cosmos, our eyes are getting sharper and our vision is extending further back in time. The newest generation of telescopes is set to transform our understanding of distant galaxies. The James Webb Space Telescope, for instance, is not just a telescope, it's a time machine. It is designed to look back to the very first stars and galaxies to a time just a few 100 million years after the Big Bang. It does this by observing in the infrared spectrum, which allows it to see the light from these distant ancient objects that has been stretched by the universe's expansion into a longer, redder wavelength. Technologies like adaptive optics on ground-based telescopes will improve image clarity, compensating for the atmospheric distortion that blurs our view. This means that telescopes could provide sharper images and more precise data, allowing scientists to analyze the structures and compositions of distant galaxies. These advancements in infrared and radio wavelengths will enable the exploration of celestial phenomena that are invisible to traditional visible light telescopes, including cooler objects and nebulae, which contribute to star and galaxy formation. But the real magic of these new technologies lies in what they promise for the future: the Mars Sample Return Mission. A collaboration between NASA and the European Space Agency aims to bring back soil and rock samples from Mars to Earth for analysis. The Europa Clipper mission will focus on Jupiter's moon Europa with its subsurface ocean. The Dragonfly mission will send a drone to Saturn's largest moon Titan to explore its unique atmosphere and lakes of methane and ethane. These missions are not just about finding answers. They are about asking better questions. They are about sending our curiosity to places we could never go ourselves, to environments so strange and so alien that they force us to rethink everything we know. The methodologies developed during these endeavors could be applied to icy moons and distant planets, deepening our quest to understand if life is a universal phenomenon. Each of these endeavors, and many more, promises to be a thrilling chapter in the story of space exploration. As our gentle journey through the tools of our exploration comes to an end, let us sit for a moment with the beauty of this collaboration between human ingenuity and the universe's quiet mysteries. We have built giant ears to listen for cosmic whispers. We have created artificial minds to help us see patterns we could never see on our own. We have launched our hands and eyes to other worlds, and we have built time machines to look back to the very beginning of the story. The instruments we create are not just for gathering data. They are a profound expression of our human spirit, a testament to our relentless curiosity. And with each new tool, with each new discovery, we are not just learning more about the universe, but we are learning more about ourselves. We are learning what it means to be a species that looks up, that wonders, and that always pushes the boundaries of the known. As we settle back into the quiet space of our thoughts, let us now turn our attention from the grand tools of exploration to a more intimate relationship, the one between our vast, mysterious universe and our small, beautiful home, the Earth. We often think of space as a distant, separate realm, but in truth our planet is profoundly and inextricably linked to the cosmos. The universe is not a silent backdrop. It is an active participant in our planet's history, its destiny, and even the life that breathes upon its surface. This chapter is a quiet exploration of that relationship, a gentle reminder that we are all in a very real way made of the universe itself. Our first thought is of a shield we don't see, an invisible protector that wraps our planet in a cosmic cocoon. This is Earth's magnetic field, generated by the movement of molten iron within its outer core. This magnetic field extends far into space, forming a protective bubble known as the magnetosphere. This invisible shield stands between us and the relentless bombardment of charged particles emitted by the sun and other cosmic sources, a constant flow of particles we call the solar wind. Without our magnetic field, these cosmic rays would collide with our atmosphere and surface, potentially causing damage to our DNA and increasing the risk of cancer and other health issues. But the magnetosphere deflects most of these charged particles, guiding them away from the Earth's surface. An interesting and beautiful result of this interaction is the aurora, the shimmering curtains of light that dance across the sky at our planet's poles. The aurora is a physical manifestation of our shield, working a beautiful cosmic light show that is a direct result of our planet's ongoing conversation with the sun. This protective magnetic field is a crucial aspect of our planet's habitability and a reminder of the intricate balance of natural forces that support our existence. But our relationship with the sun is not always so gentle. The sun, our life-giving star, has its moods, and sometimes it can be quite volatile. Solar flares, sudden bursts of radiation emitted from the sun, can release energy equivalent to millions of hydrogen bombs. While they may be awe-inspiring to observe from a safe distance, their effects can disrupt the delicate balance of our technological infrastructure. When a solar flare occurs, it produces energetic particles that can reach Earth within minutes. These charged particles can interfere with satellite operations, including navigation systems, telecommunications, and satellite imaging. Astronauts aboard the International Space Station are also at risk due to increased radiation levels during these events, necessitating protective measures while they orbit above us. Solar flares can also induce currents in power lines, leading to potential voltage spikes that may compromise electrical grids. Instances of power outages have been documented when geomagnetic storms caused by solar activity engaged with the Earth's surface systems. Thus, monitoring solar activity has become crucial for energy stability, especially in regions with high latitude where the effects of such storms are more pronounced. The sun, our giver of life, is also a reminder of our vulnerability. A quiet lesson that our technological world is inextricably linked to the unpredictable rhythms of a star 93 million miles away. The cosmos is not just a source of threats. It is also a quiet, patient gardener. The elements that make up our bodies and our world were not created here on Earth. They were forged in the hearts of stars and scattered throughout the galaxy in one of the most spectacular events in the universe, a supernova. When a massive star reaches the end of its life, it ejects its outer layers into space at incredible speeds. This explosion not only releases an extraordinary amount of energy, but also scatters the elements forged in the star's core throughout the universe. These elements, such as carbon, oxygen, and iron, are the fundamental building blocks of life as we know it. We are literally star stuff, a profound and humbling thought. Without the remnants of ancient supernovae, the rich chemistry required for life on Earth may never have formed. The supernova is a cosmic planter scattering the seeds of life across the vast emptiness of space. But a supernova is a double-edged sword. While distant ones gave us life, a supernova that happened too close to our planet could have devastating consequences. The intense bursts of radiation could strip our atmosphere of its ozone layer, which protects our planet from harmful ultraviolet radiation, potentially causing mass extinctions. Cosmic events remind us that the universe is not a silent backdrop, but a vibrant participant in our planet's history, influencing the development and extinction of life through both its fiery explosions and the elements they forge. And finally, let us consider our quiet, constant companion, the Moon. The Moon plays a crucial role in stabilizing Earth's climate and environment, primarily through its gravitational influence. As our planet rotates, it is tilted at an angle of approximately 23 degrees. This tilt is critical, as it is responsible for our seasons. Without the Moon's stabilizing presence, Earth could experience significant fluctuations in its axial tilt, resulting in extreme and chaotic changes in climate over time. The Moon is the quiet, gentle anchor that keeps our planet from wobbling wildly in its orbit. Additionally, the Moon contributes to the creation of our tides. Its gravitational pull creates bulges of water in the oceans, leading to high and low tides. These tidal movements play a vital role in shaping coastal ecosystems and influencing marine life. The ebb and flow of the tides help distribute nutrients and support various habitats, which are essential for biodiversity. The Moon's presence helps maintain a delicate balance that nurtures the conditions necessary for life to thrive. The absence of the Moon would likely have resulted in a much different Earth one that might not have sustained the same complex ecosystems and weather patterns we observe today. Thus, the Moon, though it may appear as a silent guardian in the night sky, plays an active and dynamic role in securing a stable, flourishing environment on our planet. As our minds drift off to sleep, let us carry with us this profound understanding of our place in the universe. We are not separate from the cosmos. We are a small, beautiful, and intricate part of it. The very elements that form our bodies were forged in the hearts of stars that exploded billions of years ago. We are protected by an invisible shield born from the swirling iron in our core. Our seasons, our tides, and the stability of our planet are all a direct result of our constant, gentle dance with our celestial companion. We are star stuff, protected by a cosmic shield, dancing to the rhythm of a lunar beat. The Earth is a cosmic garden, and the universe is both its gardener and its storm. This quiet contemplation is a gentle reminder of our interconnectedness, of the profound relationship between the infinite and the infinitesimally small. And in that quiet understanding, we find a deep and beautiful sense of belonging. As we drift toward the end of our gentle journey, we are not searching for final answers, but rather pausing to admire the most beautiful and perplexing questions that remain. These are the mysteries that sit on the frontier of our knowledge, the anomalies that whisper to us of a universe that is far stranger and more complex than we can currently imagine. These are not flaws in our understanding. They are invitations to quiet wonder, profound puzzles that keep the flame of our curiosity burning. Let us begin with a mystery that speaks of emptiness, of a quiet and vast nothingness. While we have talked about the cosmic web, the grand tapestry of galaxies, gas, and dark matter that stretches across the universe, we have not yet spoken of the spaces between. These are the cosmic void's immense regions of space, where very few galaxies exist. They are not a perfect vacuum, but they are as close to true emptiness as we have ever observed, vast, quiet regions that seem to defy our understanding of how matter should be distributed. Their existence raises questions about cosmic structure formation and the distribution of matter in the universe. We use powerful telescopes and advanced computer simulations to map these empty places to understand how they formed and what they tell us about the universe's past. Researchers are investigating how such vast empty spaces can exist without contradicting the principles of cosmology that predict a more uniform distribution of matter on large scales. Exploring cosmic voids has significant implications for our understanding of dark energy and the overall evolution of the universe. The voids in their profound emptiness are expanding faster than the rest of the universe. They are a perfect laboratory for studying the effects of dark energy, the mysterious force we discussed earlier that is pushing the universe apart. Observing voids can provide insights into how dark energy behaves, particularly in regions of low mass density. Through these observations, scientists can refine models that describe the universe's expansion, leading to a better comprehension of its ultimate fate. The study of voids also intersects with investigations into the cosmic microwave background, CMB radiation, the slight afterglow from the Big Bang. Understanding how voids formed and evolved over billions of years sheds light on how matter and energy interact at the grandest scales, connecting the early universe to the present day. These empty places are not just empty. They are a profound clue, a quiet negative space that is helping us understand the shape of everything. And this brings us back to the CMB radiation, the faint cosmic echo of the universe's birth. While we have captured detailed images of this cosmic relic, questions remain regarding its uniformity and any anomalies that could suggest other dimensions or aspects of the universe not yet understood. This ancient light which fills the cosmos is a remarkable remnant from a time when the universe was just a few 100,000 years old. It is almost perfectly uniform in temperature, a testament to the smoothness of the early universe. But scattered across this uniformity are tiny fluctuations, small variations in temperature that hold profound clues. These fluctuations are the seeds of everything we see today, the early slight overdensities that under the relentless pull of gravity eventually grew into galaxies and galaxy clusters. But some of these fluctuations are stranger than our current models can explain. For instance, there is a large cold spot, a vast region of the sky that is significantly colder than its surroundings. Could it be a colossal cosmic void? Or could it be a sign of something even stranger, a whisper from a parallel universe bumping into ours? The fluctuations are not merely statistical noise. They are profound puzzles that challenge our scientists to rethink the conditions that led to the intricate structure we see today. The continued exploration of cosmic background radiation reveals not just the history of the universe, but also the mysteries that linger within it, inviting a closer look at the universe's origins and destiny. Now let us turn our attention to the ripples we talked about earlier, the gravitational waves. While we have confirmed their existence and detected them from colliding black holes and neutron stars, we are only at the very beginning of this new kind of astronomy. The potential of these waves opens up new avenues for understanding the fabric of space-time. Gravitational waves are a new sense, a new way of listening to the universe. What else can they tell us? Can we use them to see events that are hidden from light? Like the moments just after the Big Bang, a time when the universe was too hot and dense for light to travel freely. The universe at that time was opaque to light, but transparent to gravitational waves. The hope is that by listening carefully, we might be able to hear a sound, a tremor from that very first moment of creation. The potentials and implications of these waves are profound, and scientists are refining their instruments and experiments to explore these ripples in more detail, hoping they might unveil secrets about the early universe or the fundamental workings of gravity itself. The pursuit of these anomalies represents a thrilling frontier in astrophysics, promising to reshape our understanding of the universe. And finally, we must sit with the most profound question of all, the one that whispers to us of an ultimate ending. We spoke earlier of dark energy, the mysterious force driving the universe's accelerating expansion. What does this mean for our future? As researchers continue to delve deeper into the mysteries of the universe, they may soon uncover discoveries that fundamentally alter our understanding of reality, including its fate. While the nature of dark energy remains elusive, its effects are already being felt. The accelerating expansion means that the universe is not just growing, but its different parts are moving away from each other faster and faster. This leads to three possible scenarios for the ultimate fate of our cosmos. The Big Freeze suggests that the universe will continue to expand forever, growing colder and lonelier as stars burn out and galaxies drift so far apart that their light can no longer reach each other. The universe will become a dark, silent, and empty place. The Big Crunch posits that the expansion could eventually halt and reverse due to gravitational forces causing the universe to collapse back into a singularity, a fate that places cosmic cycles at the forefront of discussions about existence and rebirth. The third hypothesis is the Big Rip, which speculates that dark energy could grow stronger over time, tearing apart galaxies, stars, and ultimately even atoms themselves. These are not just scientific theories. They are profound, quiet meditations on the ultimate ending of our cosmic story. Each of these remaining mysteries, from the emptiness of the voids to the cosmic echo of creation, from the subtle tremors of space-time to the ultimate fate of all things, is an invitation to quiet wonder. They are a testament to the fact that for all we have learned, there is so much more to discover. We are not at the end of the road. We are at the very beginning. The universe is a vast and ancient book, and we have only just learned to read the first few sentences. To sit with these questions, to embrace the unknown, is to participate in the most beautiful and profound adventure of all. As we come to the final leg of our gentle journey, we must turn our attention away from the stars and the galaxies and back toward ourselves. For the act of exploring the universe is not just about learning what is out there. It is about learning what it means to be here. The insights we have gained, the mysteries we have embraced, and the questions we have asked all have a profound impact on our sense of self, our place in existence, and the ultimate destiny of our species. The most immediate effect of contemplating the vastness of the universe is a sense of cosmic humility. For millennia, our ancestors believed that Earth was the center of creation, a special and unique place at the focal point of the cosmos. But the Copernican revolution changed all of that. We learned that we are not at the center, but are simply inhabitants of one small planet orbiting one small star in a spiral arm of one of billions of galaxies. This humbling realization can evoke a range of psychological effects, deeply impacting our sense of self and our place within the cosmos. Faced with galaxies that contain billions of stars and planets, individuals often experience a humbling recognition of their own insignificance in the grand scheme of things. This can lead to a profound shift in perspective, encouraging a desire to understand not only the universe, but also the intricate connections that bind all life. This sense of cosmic connection is further reinforced by the idea that we are all quite literally star stuff, our bodies made of the very elements carbon, oxygen, iron, forged in the hearts of ancient stars that exploded billions of years ago. Our existence is a direct, tangible link to the cosmic story, a beautiful testament to the fact that the universe lives on within us. But with this sense of awe and connection also comes a new set of responsibilities. As we venture further into the cosmos with plans for human habitation on other celestial bodies, we must confront profound ethical considerations. The search for life beyond our planet, for instance, raises complex questions about what we do if we find it. Do we have the right to interfere with a developing ecosystem on Mars or Europa? How do we ensure that we don't contaminate these pristine environments with our own earthly microbes? This is the core of planetary protection, a quiet, thoughtful commitment to minimizing our impact on other worlds. Furthermore, the possibility of colonizing other planets invokes ethical debates about exploration and exploitation. As we look outward for new homes, considerations about ownership, environmental sustainability, and the rights of potential extraterrestrial life forms the crux of a new philosophical dialogue. These discussions could lead to novel frameworks for how society functions, shaping not only our destiny, but also the moral compass guiding humanity's advancements in this new frontier. The journey into space is not merely a leap into the unknown, but a transformative voyage that holds the potential to redefine who we are as human beings. The act of space exploration also serves as a powerful catalyst for progress here on Earth. The technologies and scientific breakthroughs that we develop for cosmic exploration often have far-reaching applications in our daily lives. For example, advancements in imaging techniques and data processing initially designed for studying distant stars and galaxies often find their way into medical technologies, environmental monitoring, and telecommunications. This cross-pollination of ideas fosters an atmosphere of curiosity and encourages the next generation to pursue careers in science and engineering, which can ultimately drive the economy and enhance societal progress. The quest to explore outer space also encourages global collaboration. International space missions, like the International Space Station and the Event Horizon Telescope, highlight the need for countries to work together toward common goals. This unity can transcend barriers, promote peace, and cultivate a shared sense of humanity as we all look toward the stars. The same spirit that drives space exploration can be applied to addressing global challenges like climate change or humanitarian issues, reminding us that we are all on this pale blue dot together. Finally, the greatest influence of cosmic exploration is on our collective human destiny. As we continue to make strides in understanding our universe, we may also experience a heightened sense of responsibility toward our planet. Discoveries that illustrate the fragility of celestial bodies or the interconnectedness of ecosystems prompt society to rethink its priorities. The realization that Earth is but a small oasis in a vast universe can evoke a more profound respect for our home and incentivize actions that promote sustainability and conservation. With each revelation from the depths of space, we are reminded of the importance of cherishing our unique world and nurturing it for future generations. Moreover, the act of looking up at the stars is a quiet contemplative act that links us all. It is a shared human experience that has existed since our earliest ancestors first gazed at the night sky. In that quiet act of wonder, we find a sense of continuity, a connection to our past, and a profound hope for our future. The universe is not just a place we exist in, but a mirror in which we learn to see ourselves. It is a story in which we are both the reader and a character, and the greatest adventure of all is the one we are just beginning to write.